Hi, my name is Eric Hendricks. I'm from Providence St Mel School, and I would like to spend some time with you today to discuss some math problems that some of my students are working on. Maybe you'll find it interesting. We'll try to connect it to real world type examples, and then hopefully at some point you'll get a chance to let me know how you feel about the problems that I've done. All right, so that said, let's just jump right into it. All right, so we've got a problem here. And basically it might not look like a problem. All right, so let's take a look at this here. All right, so we've got some data. Okay, so we've got some data here. All right, so we've got the 0, 50, the point, let's call this an x value and a y value. We've got the point 055. We've got the point 145. We've got the point 235, 325, and so forth and so on. The x value and the y value could also be time. You know, the variables don't really matter here. The variable could be time, and let's say the variable could also be something like speed. All right, so I know I've got the variables x and y here, but this could mean at time 0, something is traveling at 55 feet per second. At time 1, something is traveling at 45 feet per second. So though I have the variables x and y, the x can represent something real, some real world, something very relevant to our society. And same thing with y. So what we want to do is we want to take this data and we want to write an equation that models this data. We want to write a mathematical equation that represents this data. And with a mathematical equation that represents this data, what we can do is something called extrapolate the data and predict what's going to happen. We can predict what's going to happen at time 10 that you cannot see. We want you to predict what's going to happen, let's say at time 10 or at time 50. All right, at time 50, you don't want to just count by 1 and then on this bottom row continue to decrease 5 at a time. You don't want to have to do that 50 times or more. So what we're going to do is come up with an equation that models this data and then do some predicting of what's going to happen at time 10 and at time 50. All right, so that said, let's just jump into it. The thing I'd like you to be able to see here is I'd like you to be able to see the y values here are decreasing by 5. So you're at some number, you're decreasing by 10. So you're at some number, you decrease 10, and you continue to decrease 10 to get to the next number. You're subtracting 10 multiple times. The way you write that in math, is to write that as a product, negative 10x. The continuous subtraction of a number can be rewritten as the multiplication, of whatever it is that's being repetitively subtracted. All right? So let's work with this. So again, we're subtracting 10 to go from here to here. We're subtracting 10 to go from here to here. Subtracting 10 over and over again. That's repetitive subtraction. The way you write that is negative 10, that which is being repeated, times x. All right? So the thing we're going to do now is if x is equal to 0, we want to get 55. All right? So what we can do here is if we put a 0 here, we get negative 10 times 0, which is 0. All right. But what we want is we want to put in 0 and get 55. So what we can do is add 55. And what we end up with is y is equal to negative 10x plus 55. So if we put in 0 now, we get negative 10 times 0 plus 55, which is 55. If we put in 1 here, negative 10 times 1, you end up with negative 10. You end up with negative 10 plus 55, which is 45. We put in 2, negative 10 times 2 plus 55, you end up with negative 20 plus 55, which gives you the negative 35. So I think what you'll discover is this equation now models the data that we have. And now that you have an equation that models the data that we have, you can now make a prediction as to what your y value is going to be here at x is 10. All right, what you can do here is you can take your equation, which is negative 10x plus 55, and you can substitute in 10. You have negative 10 times the substituted 10 plus 55. You end up with y is equal to negative 100 plus 55. And I think we can see that your final answer will be negative 45. So what that does is it saves you the time of having to decrease 10 at a time for another 5 x values. You don't have to go to 6, 7, 8, 9, 10 to get this y value. And you don't have to do that for 50 either. To get the y value at 50, you can use this equation because this equation models all of this data. All right, so you could substitute in 50 into the equation. So we got y is equal to negative 10 times 50 plus 55. You get y is equal to negative 500 plus 55. And you get y is equal to negative 445, if my arithmetic is correct. All right, so big picture, what are we doing here? Big picture, you're given data, all right? You're given data, and what you want to do is you want to take that data and you want to model, you want an equation that models that data so that you can use that equation to predict what's going to happen in the future. The question might ask if the top row is time and the bottom row is speed, the question might ask something to the effect, what is the speed at a certain time? What's the speed at a certain time? And what you would do is you would take the time that they gave you, you'd substitute that time that they gave you into your linear model, and you would be able to answer that question. All right, enough of that. I want to move on. I want to move on to another example. Let's say we've got another problem that we want to take some data and we want to create a linear model to represent that data. All right, so let's say, well, let me get this drawn first. All right, so let's say we have the number at, let's say we got x and y again, but let's say x can represent days. All right, x represents days, and let's say y represents degrees Celsius. All right, and after the first day, the degrees Celsius temperature is 16 degrees. After the second day, the temperature out is 19 degrees Celsius. After the third day, let's say 22 degrees. After the fourth day, let's say it's 25 degrees. After the fifth day, say it's 28. And I think you see the pattern. After the sixth day, let's say it's 31. I think you see the pattern. All right. And let's say the question would ask, what is the temperature? What is the temperature in degrees Celsius after, what's the temperature in degrees Celsius after, assuming that the model remains linear after 11 days? All right, now, true enough, you can just continue to count by, in this case, 3. I understand that. But the thing that I'm trying to show you is that not only would you be able to find the temperature after 11 days, with a linear model, you can find the temperature after any number of days. So that would be the benefit of coming up with a linear model that represents this data. All right, so in the other problem, there was a decrease in 10 to get from one number to the next. Here, I'd like you to be able to see there's an increase of 3, a constant increase of 3. So the way we write the repetitive addition of 3 is similar to what we did in the other problem, where we have 3 times x. The way you write the addition of 3 repetitively is by multiplying. And what we want to do here is we want to substitute in a 1 and get 16. We want to substitute a 1 into this linear model and get 16. Hopefully you see that substituting in 1 right now would not give you 16. You'd have to add 13 to the result of the 3 times the 1 to guarantee getting a 16. So your equation is y is equal to 3x plus 13. That's the linear equation that represents this data. If you put in 2, 3 times 2 plus 13, you would get 6 plus 13, which is 19. If you substitute in 3 into this linear model, 3 times 3 plus 13, you get 9 plus 13, which is the 22. So this equation represents each of these points. And now with that equation, what you can do is you can answer the question after time 11. In other words, you'd substitute that 11 right there. You would take y is equal to 3 times 11 plus 13, and you'd get 33 plus 13, and you'd get 46. You get 46. So the answer to the question, what's the temperature after 11 days? It would be 46 degrees Celsius. All right, so enough of that. Enough of that. What we like to do now, that was sort of a prerequisite exercise to understanding what we're about to do now. In real life, over time, things don't increase by 3. Things don't just continue to decrease by 10 repetitively like that. You have to be able to be flexible enough to be able to come up with equations even though your data is not increasing repetitively. It's not increasing at the same rate of change or decreasing at the same rate of change. So really the whole purpose of today's class is to address problems that don't have a constant rate of change. It's called creating a best fit equation. Okay, so that's the goal for today. Let's jump into it. Let's get rid of this. And let's present a problem that I've actually done before. I've done this problem before in shows in the past. All right, so let's say we've got x again, y again. Let's say we have 4 pieces of data this time. All right, let's say we have 4 pieces of data. All right, so let's say we have at 0, we have 100. At time 1, we have 50. And let's say at x is 2, we have 100. And at x is 3, we have 200. So clearly, you don't have the constant rate of change that we experienced before. In fact, if I were to graph this very, very quickly, and let's say count by 50, 100, 150, 200, and then we got 0, 1, 2, 3. If I were to graph this, we got 0, 100. Okay, so we got 0, 100. We've got 150 to 100. You can see that this is somewhat scattered. 3, 200. This is somewhat scattered, okay? So it's not perfectly linear. You don't have the constant slope, sometimes it's called, that we had in previous problems. However, you can still come up with a best representation of this data, and that's the whole purpose of today's lesson. And the way we're going to do that is to follow some of the rules that we might have learned in algebra. In algebra, if you had, let's say, a 0.32 and a 0.41, what you would do in algebra, just making up those points, by the way, is you could first find the slope. And you'd find the slope by taking the change in the y values, 2 minus 1, and then you would divide that by the change in the x values, 3 minus 4. And your slope would be 1 over negative 1, and this simplified would give you negative 1. You would then take that slope and substitute it into what's called the slope-intercept equation, and you would take one of the points, it doesn't matter which one, you would take one of these points, you would substitute in the y value, I'm choosing this point here, and then you would take the slope that you got from the previous step, you would take that slope and multiply it by the x value, 4, I'm not using this point at the moment, plus the y-intercept, you'd get 1 is equal to negative 4 plus b, you add the 4, and this is something that maybe you learned in Algebra 1, and you get the y-intercept is 5. You get the y-intercept is 5, and you'd now have your equation, y is equal to negative 1x plus 5. So what you learned in Algebra 1 is going to be what we build on now in this new topic called producing a regression equation. Sometimes it's called a best fit equation. All right, so this is what you're going to have to remember as far as what we are going to do as far as taking this to the next level. We're going to find a slope, just like we did in Algebra 1. And after we find a slope, we're going to find a y-intercept, just like we did in Algebra 1. All right, so I'm going to erase this and we're going to move on to our problem. All right, so let me write this data again. Don't forget, we're going to find the slope, just like we did in previous classes, and then we're going to find the y-intercept. I hope it's clear. I hope it's clear what I am saying. All right, so we got x values and y values. I had this written down before. I'm just going to write it down again. We got 0, 1, 2, 3, and then we got 100, 500, 50, 150, and then we got 2, 100, and then we got 3, 200. That's what I had before. All right, so let's find the slope. It just turns out that the slope is going to look a little bit funny. It's going to look a little bit funny, but the equation that we need to find the slope is, let me put this a little bit lower. The equation for our slope is going to be our equation for our slope is going to be x, y bar, we'll tell you what that means in a minute, minus x bar, y bar. All right? So those bars mean averages. Those bars mean averages. And this is divided by the standard deviation of x. All right? So we're not just finding the equation between 2 points anymore. The beauty of what we're doing right now is finding the equation. The beauty of what we're doing right now is finding the equation of an infinite, potentially infinite number of points. We're finding the best equation that models potentially an infinite number of points. All right? So now what we're going to do is this bar here means average. Find the average of the product of x and y. This bar here means find the average of the x's. This bar here means find the average of the y values. So I think what might be helpful for me is to just rewrite this. I hope you don't mind. I'm just going to rewrite this in a little bit different way. I have 0, 100. Just write my data vertically. I've got 150, 2, 100, and 3, 200. All right, so xy, the product xy, just requires that you take the product of all the x values and all the y values. 0 times 100 is 0. 1 times 50 is 50. 2 times 100 is 200. 3 times 200 is 600. All right. And what we're going to do is we're just going to find the average of the x's. All right. The average of the x's, if you add 0 plus 1, that's 1, plus another 2 is 3, plus 3 is 6. So you want to find the average, you take 6 divided by the 4 terms, and that's going to be 1.5. So that is x bar. That's the average of the x's. How about the average of the y's? Let's add these up. This is 100 plus 100 is 200, plus that 200 is 400, plus the 50 is 450. Let's divide that 450 by 4. I don't have my calculator with me, but let's try to do it the old-fashioned way. 4 goes into 450 one time. That's 5, 1, 4, 1. That goes in twice. You get 8, 2, 0, 112.5. So our y bar, or the average of all the y values, is 112.5. All right. We're going to use these to find the slope. All right. So how about xy bar right here? We need xy bar. Let's find the average of xy's. That's 800 plus 50 is 850. Let's divide that 850 by 4 the old-fashioned way. I didn't bring my calculator today. Next time I'll bring it. So it goes in twice, 8. It goes in one time, 4, bring down to 1, 0, you get 2. It's 8. You probably can't see what I'm writing here, but I believe we get 212.5. So we took the 850 divided by 4, and we got x, y bar is equal to 212.5. 212.5. We are going to find the slope just like we did in Algebra 1. In Algebra 1, we found the slope first. So that's what we're going to do here. So xy bar is 212.5 We got that from right here. Minus x bar, we got that right here. X bar is 1.5 times y bar is 112.5. And all of this needs to be divided by the standard deviation. Standard deviation is something that possibly we'll talk about next time. We're not going to have time to actually go through the process of calculating it by hand. Fortunately, I did, before the show, I calculated the standard deviation on my own, and I ended up with root 5 over 4. All right, root 5, actually root 5 over 2. Sorry about that. Thank goodness I did that, okay? Otherwise, we wouldn't have time to finish this problem. And the standard deviation has to be squared. So you might be asking yourself, where in the world did that come from? That is something called standard deviation that we'll have to talk about next time, how we calculated that. All right, so I actually need a calculator here. That numerator, I think I might need to use my phone. I think I might need to use my phone to actually calculate this out. And wouldn't you know that technology, hopefully I can, all right. Just give me a minute, please, while I look for the calculator feature on my phone. Yeah, I didn't bring my calculator. All right. Well, okay. Fortunately, I did this problem before the show started. And if you put all of this in the calculator, you put all this into the calculator, and I'm sorry I don't have my calculator with me. Oh, there we go. I've got it now. So I've got my calculator. So what I'm going to do is I'm going to take 212.5 minus, now I'm going to take 1.5. I'm going to take 1.5 times 112.5, and I got 168. Oh, okay. Yeah, okay, I got forgive me. I need to take 212.5 minus 168.75, and that's going to be divided by 1.25. 1.25. You square the radical 5, you get 5. And then you square the 2 and you get 4. So that's going to be 1.25. So if you divide that out, divide it by 1.25. All right. So I need to take 212.5. I'm going to subtract 168.75, and I end up with 43.75. Divide that by 1.25. All right, and I get 35. So the slope is 35. The slope is 35. I hope this is clear. I went from here to here. Okay? So the slope is 35. Now, just like in Algebra 1, after you find After you find the slope, you then find the y-intercept. I'll do that right here. So our slope is 35. So now what you're going to do is you're going to take your slope-intercept equation. You're going to substitute in an x value and a y value. Turns out that our x values and y values are the means of the x's and the y's. You're going to take the 112.5 is equal to the slope, which is 35, times the 1.5 plus the y-intercept. You end up with 112.5 is equal to, let's put this into our calculator here. All right, so we get 35 times 1.5. I got 52.5 plus the y-intercept. Just like in Algebra 1, we found a slope first. And now we're finding the y-intercept. So now I'm going to take that 112.5 and subtract the 52.5. And I get 60. The y-intercept is 60. So now you have the equation. You have y is equal to, this is the best fit equation for the data that didn't have that constant rate of change. So we have y is equal to 35x plus 60. Y is equal to 35x plus 60. So you could ask the question, you could answer the question, if this data were to continue to progress the way it is now, you could use this equation to approximate what's going to happen at time 4. You could use this data to approximate, and I really emphasize the word approximate, what's going to happen at time 4 or 5 or 10 or 30, depending on how long you sort of anticipate that the data is going to continue to react the way it is right here. So I hope that was understandable. I hope that was clear. This is called that's called a regression equation. It's called a regression equation, and it is a statistical topic. You might see it in statistics. I've mentioned a couple classes in this show. When we talked about y is equal to mx plus b, that's an equation that tends to be introduced in the Algebra 1 course. What we talked about today might be a topic that you see in an Algebra 2 course, or even possibly a statistics course. So I hope that was clear. I hope that was understandable. I think that's all we have time for today. In a class that I've had, a show that I've presented in the past, if I still have time, I'm not sure if I still have time. All right, in a show that I've presented in the past, to find the slope, I used a different equation. I think that's about all we have time for. So I appreciate your attention. I hope you enjoyed. I hope you learned something on this topic of regression equations, sometimes called best fit equations. Take care and good luck. Keep studying. Never quit in your math classes. God bless. Take care.